Hello students, welcome to my Abhyas. My name is Sahana Case and I am your physics educator. So we were in the topic electrostatic potential and capacitance, and we have seen the potential due to system of charges in the last session. And in this session we'll be looking into the equipotential surface, the characteristics of that, and also the relation between the electric field and electric potential. So we have been listening about electric field and electric potential a lot. So in today's session, we'll start with the equipotential surfaces, and after that we'll look into the relation between the main two quantities, that is electric field and the potential. Okay. So moving on to the properties of equipotential surfaces. So the word itself says that is equipotential. What do you mean by equipotential? Equal potential, right? Surface in the sense the whole area, whatever is that. So on the surface there is equal potential. Right. So what does that mean is on the complete, like due to a point charge, how does the potential is equal? How is the potential equal? And due to two charges, how will be the potential influencing? So we'll look into it. Coming to the first point, we'll see what is equipotential surface. So any surface with same electric potential. So it is any surface with the same electric potential at every point is called an equipotential surface. So any surface with the same electric potential, we call it as what? We call it as the equipotential surfaces. You have to remember this, and this is a very important concept because this concept is mainly highlighted in your CET and NEET questions. Okay, the questions come from this topic, that is equipotential surfaces. So what is that? Any surface with the same electric potential, we call it as what? Like at every point on the surface. For example, if I take a point charge, so I just consider a point charge. So once I consider a point charge, what will happen? See, I have said you the same electric potential. Due to the point charge, we get the concentric circles, right? The field or electric field, you can say, will be in the terms of concentric circles. Now, due to the point charge Q, okay, so if I take a charge on this, okay, or due to the point charge Q, what will be the potential on the surface C? How can I calculate that? Okay, I'll just take it as VC. Okay, moving on to the next. Here I'll take another point. Okay, so if this is of 1 volt, okay, then here also what happens? Because of the charge Q, the voltage will be the same, that is again 1 volt itself. Okay, but it won't be the same here because on this surface, what is happening? The distance is getting decreased. So if there is a decrease, that is, we know that E is inversely proportional to 1 by r square, right? So if it is E is inversely proportional to 1 by r square, then the distance decreases. Then what happens? Electric field varies. So if electric field is varying, then obviously on this surface the potential will be different, but that is on this surface the potential will be the same, but not as the C orbit. For example, if I take this as B, okay, then the potential VB will be 2 volt, you think it, and here also it is 2 volts itself. On that potential, what happens? On that surface, that is on that orbit, the potential will be the same. Clear? So that is what we call it as equipotential surfaces. Coming to the next, electric field is always perpendicular to the equipotential surface. So here this is very important because as we derive a equation further which relates electric field and also electric potential, then what is it? Electric field is always perpendicular to what? To an equipotential surface. So if it is equal to equipotential surface, then the work done in moving that charge will be 0. Why? Because the electric field is it is always perpendicular. If it is always perpendicular, then the work done, that is the perpendicular work done, will be 0, right? Because we know that V is equal to what? W by Q naught, right? If I am bringing the charge which is perpendicular to the electric field, then what happens? This potential becomes 0, or you can say the the potential on that surface, equipotential surface, will be 0. Okay. I hope the first and second sentences are clearly, thoroughly understood by you people. Next, third one. Okay, equipotential surface help to distinguish. So these help us to distinguish the regions of strong field from those of the weak field. So equipotential surfaces give you an overview on how the field is varying, that is the electric field is varying, like where are the strong fields and where are the weak fields. Okay, because it is perpendicularly influencing the surfaces. So if it is perpendicular to the surface, then obviously you can see that if there is a weak surface or a strong field, it is noticeable. Okay, moving on to the fourth one, equipotential surfaces tell the direction of electric field. Yeah, this is true, because in the next case, like we will be solving some cases. In that you will know how can we prove that the direction of the field will be taken. Okay, and no two equipotential surfaces intersect each other. So this is also important, because there are we know that, right, the electric field is only one dimensional, that is it does, the electric lines of force do not intersect. Similarly here what we have, there is the equipotential surfaces do not intersect. Clear? So these are the four, and next we have other two properties. So what is the first property? The first property or the definition of equipotential surface is any surface with the same electric potential. So any surface which has the same electric potential at every point, it is called as what? It is called as an equipotential surface. Moving on to the next, electric field is always perpendicular to the equipotential surface. Hence, the work done in bringing the charge perpendicular to the equipotential surface will be 0. After that, we have equipotential surfaces help us to distinguish between the strong field and the weak field. Why? Because the electric lines of force are under act. Okay, and then we have the fourth one, where equipotential surfaces tell the direction of the electric field. So these surfaces tell the direction of the electric field, and also what do they do is they do not intersect with each other. So if there are two equipotential surfaces, then they do not intersect. Okay, moving on to the next slide, what we have, because once we know the characteristic, I can easily tell you how it varies in the point charge, in a linear charge, and also when the two charges are taken, that is the surface. Okay, next, coming to the fifth point. In case of point charge, okay, if there is a point charge, then equipotential surfaces are concentric spherical shells. Obviously, I just took an example here. So it was Q charge and the equipotential surfaces was taken in terms of spherical surfaces, right? Because how we take electric field? We take electric field in terms of spherical shells itself. Similarly, this is the same. Okay, that is in case of a point charge, equipotential surfaces are concentric shells or concentric circles. Then for a uniform electric field, so if there is a uniform electric field E along x-axis, then the equipotential surface are normal to x-axis. That is, it may be parallel to y or z, because electric field is always perpendicular to the area or the surface, right? So if it is perpendicular to the area or the surface, then what you can say, it is the planes are parallel to the yz. That is, if x-axis is taken by the equipotential surface, then y or z plane gives you the what you can say, the uniform electric field E, because always electric field will be taken in terms of the perpendicular lines. Clear? Moving on to the next, we have the importance, like, you know, when a point charge is there, how the equipotential surface is taken, and then leading on to that, we'll just study on different surfaces how the electric field or equipotential surfaces are taken. Moving on to the first, equipotential surface is a surface with a constant value of potential at all the points on the surface. So you can see here there is a positive charge, right? So if there is a positive charge, then what is happening? There are concentric circles. Concentric circles are around the charge. So as there are concentric circles, why did we get concentric circles? Because we know that whenever a positive point charge is taken, so whenever a positive point charge is taken, then what we say, the electric lines of force or the electric field is outward, right? So if we take it outward like this, right? So the electric lines of force or the electric field is outward. Okay. So what I do is I start interconnecting these. So once I start interconnecting these, I get a surface. That is first, then I have the second one here. Okay, and I have the third one here. Okay, this same image I have drawn here. I have just put the image of that. So here you can see there we have V1, V2 and V3. So V1 is of the first shell, the potential of the first shell. V2 is of the second shell and V3 is of the third shell. You can see the electric field is exactly perpendicular to those concentric circles. It is making 90 degrees, right? In all the terms, it is making 90 degrees. So if it is making 90 degrees, then the potential on this V1 will be the same. Okay, the potential on V2 will be the same. And the potential on V3, wherever you take, on whichever point you take on V3, it will be the same. So for example, if I take here point A, I'll take at point A, and here at point B, the potential will be the same. Okay, and at point C and at point D, the potential will be the same. But the potential will be different if you take the potential at A and the potential at D. Okay, the potential will be different if you take it at A and D. Clear? So that is how the equipotential surfaces are considered in a point charge, whenever you consider a point charge. Moving on to the next, we have in the linear charge, or whenever it is moving through a linear surface, how is electric field and the surface taken and how the potential have to be considered. So you can see here there are three surfaces and the electric field is moving through those surfaces, right? So the electric lines of force or the electric field is exactly perpendicular to the surface, right? You can see here it is exactly perpendicular to the surface. Means what is happening? It is giving me 90 degrees here. So if it is giving me 90 degrees, then what I can say? The potential across the whole surface is the same. Okay. For example, if I take a point A here and if I take a point B here. So if I take a point A here and if I take a point B, then the potential at A is equal to the potential at B. Clear? So, but if I take a point C here and point D here, C and D have the equal potential, but A and C do not have the equal potential. That's why we have given 1, 2, 3 names, that is V1, V2 and V3, because the potential is not the same, or else we would have just named it as V. Okay, in all the three cases we would have named it as V. Clear? I hope you are understanding this. Moving on to the next, whenever it is in the linear charge, the electric field is exactly perpendicular to the planes. So as it is exactly perpendicular to the planes, it is making 90 degree, then the potential will be the same on all the surfaces. That is, whenever you consider individually the surface, that is the potential will be the same. Clear? Moving on to the next, we have when we consider two charges. Okay, when we consider two charges, how is it? So once I take this negative and positive potential, okay, once I take the negative and positive, the electric lines of force, that is separately I have taken here. Obviously concentric circles will be there. Then what happens? Here you have V1 for example, and if this is V2 and if this is V3, this is V4. So when I consider the surface, what happens? So when I consider the surface, it will be looking like this, because positive plus Q and negative minus Q, right? So it is plus Q and minus Q. So once it is plus Q and minus Q, what is happening? The electric lines of force will be exactly perpendicular like this. Okay, for this and for this also it will be like this. But here you will be having the outward lines of force, here you will be having the inward. That's why there will be a force of attraction. So as there is a force of attraction between those two, then the equipotential surface will be like this. Okay, because they will be combined because of the attraction force. Clear? I hope you have understood the concept of equipotential surface. Equipotential surface means on the surface, whenever you calculate the potential will be the same. So that type of surfaces we call it as what? The equipotential surfaces. Clear? Moving on to the next.